So here we also have, the different variables, right? E is electric field, rho is the charge. Again, we'll talk about this in the coming slides.
Oh.
But all these units you see here, right? They are all in, they are all SI units.
Yeah.
I believe. But again, when you talk about units, especially about magnetic fields, you probably know that magnetic field, a lot of units, Tesla, Gauss, ampere, all this. So again, it depends. If you use SI units, I think you should stick to SI units. If you change units around, then you might not get the right answer.
Correct.
Right. So, okay. Right. Let's look at this Gauss's law for electric fields. Okay. So what do we have here? We have called del.
Okay.
We have another one called, another thing here, dot. Okay. Then we have
Epsilon.
Yeah.
So what is that? Permittivity?
Epsilon is electrical permittivity, and we'll talk about that in a bit. Or electrical or dielectric.
Yeah.
Gates.
E you already mentioned the electric
E
field.
is electric field, yes.
What is rho? Charge density.
Yes. So this is rho, which represents volume, charge, density. Okay. Now, so let's start with what we know. Okay. We know about electric fields.
Yeah.
What?
Something I've studied.
Yes. Something I've studied too. But if you look at the equation, it's probably easy to start with what we know. Electric fields. Okay, if you talk about electric fields, you probably heard about positive charges.
Yeah.
Okay. And negative charges. Now, if you look at the electric field, right, emanating from a positive charge, you'll find that
it will land on a negative charge.
That's true. Or you kind of.
No. This I studied in +2, I think.
So you see that these electric fields, they diverge, right, from a positive charge. So electric fields are diverging out from a positive charge. But if you look at a negative field, what you see is they converge. At a negative charge.
Yeah.
Okay. So then diverge and they converge. Now, as you mentioned, if you bring a positive charge, goes to a negative charge,
nearby, what are these lines?
These are the
electric field lines.
All right. So individually, if they're far apart, you'll see that these electric field lines, they will diverge out, not diverge, but diverge from positive charges and converge to negative charges, but independently, right? But then if you have two charges coming together, you'll see that these electric field lines terminate at a negative charge.
Got it.
Okay, so that's I think that's, we all know that. You probably know this from high school. Okay. Now this dot operator.
It's a dot product.
But this is also called divergence. So now do you kind of get the point here what divergence is? I mean, we'll talk more, but we're talking about divergence at a
closed surface.
No. If you look in the field, you're looking at divergence at a single point.
Okay.
Right? Now, flux, on the other hand, we're talking about the area. Like flux through an area. But if you're talking about divergence at a single point. Okay. And we also have positive divergence and negative divergence. So in that sense,
So if you take a point charge like this, the first one is positive divergence.
yes, which we call a source. Now, if you're talking about negative charges, right?
It sinks.
It sinks. Yes. Call it the sick. Okay. So far, so good. Right? So far, I think we can all understand what it means. So, but if you look at divergence, then this nabla character. So this is called we call it del, but the symbol is called nabla. Then nabla, what it is, if you just take that operator, okay. Now you see here I, J, and Z. Okay. Now if you take a Cartesian coordinate x, y, z, right? These are basically unit vectors
on those
axes. Okay. But now we also have, but this doesn't really mean anything because it's not. So now we need to use this operator on something, right?
So it's a derivative.
It's a derivative. So
on each axis.
But in this case, it's just a notation. We're not really using it on any vector.
Yeah.
Now, in this case, we are going del. Now we're using it on the electric field.
Yeah.
So then, what happens? You have now the electric field. I don't know. I did not point it. Let me erase this. Now, if you talk about E, right? E also, there's a component in the
each direction.
Yeah. I, J, M. Sorry, this it's I, J, K. That's doesn't matter, but just to be easy to understand. Okay.
Yes.
Now, but what we have here is del dot E. Okay.
Del dot epsilon E.
Del dot epsilon E. We'll come to epsilon later because remember, as I mentioned, we assume that this particular property is the same.
Oh, okay. So it's just a number.
It's just let's say in this case, let's consider it a constant. Okay. So then, in that case, del dot E, as you said, you already mentioned that, is now you have unit vector times a unit vector, right? And del E x over del x plus j del E y over del y plus, I think I used k del B z del z. Now we know unit vector is 1, right? So then we are left with y plus del B z del z. So as you mentioned before, this whole del dot E, right, is the derivative of this electric field in 3 different directions. Okay, so that's what it means. So
now earlier you said from a point source, yes, the field is coming out.
Yes.
So if I take
very, very small.
Yeah. So if I take del dot E for that,
yes,
it will be a positive number.
If you take del dot E for a point,
yeah,
it will be positive. Yes. But when I mean a dot point, I mean that
it can have some volume.
that area is very, 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 very small.
Yeah. But even if it has a volume, it may be fine.
Yeah, it could have a volume as well, right? Yes. You're talking about the amount that of the field that diverges within a certain volume.
Yeah.
Yes. So okay. I understand what you're trying to get at. we'll get to that. We'll get to that. So you've been talking about this electrical permittivity. So this is epsilon, right?
Yeah.
So if it's electrical permittivity. Now, this is basically the response of a material to an electric field, right? So in another way of saying it is how much a material polarizes when exposed to
an electric
field. Okay, so so if you, the easiest way to explain this is, all materials have atoms inside, right? But they are probably packed tightly together. But let's say you have a certain material, okay, and let's say you have these atoms. Stop. Okay. And then you have, say, plus minus. Something like this. Plus and minus.
They are random
orientation. Now, imagine, let's say you expose this.
What is that? What are those on the sides?
Let's say they are
two conductive
plates of a capacitor.
Two conductive plates.
Two conductive plates.
Okay.
And you have plus charge on one side, negative charge on the other side. And then let's say this creates an electric field between these two plates. And this material is in the middle.
In between.
Okay, so then you have an electric field this way. Okay. What's going to happen to this?
The one inside?
The one inside.
Maybe like the compass. To try to
reorient.
Yes.
Correct. So now you have an electric field. Before it was in random orientation. Now what's going to happen is this is going to, I should draw this bigger so it can be clear. Let's say it's like this. They all should be the same size. So then you'll have now permittivity then is how easy a certain material will kind of aligned when
an external electric field is applied.
Yes, in the presence of an external. So that's what this epsilon is. Right? So we now know del dot E. We've covered these two. All of that is equal to this volume charge density.
Volume charge density. Which one?
That? This is
rho. Rho. Yeah.
Right.
So this epsilon E also has got another term, no?
Yes, it's also called dielectric permittivity.
That is epsilon itself. But epsilon into E, we also put
we're talking about
D.
D equals epsilon E. This one.
That's the electric flux.
D is electric flux. And E is obviously
yes,
correct. So then all of this, so basically the change in the electric field in all three dimensions times how easily you can orient right? A certain, let's say, material is equal to a volume charge density. Now, you talked about area before, did you? So, imagine this is 3D.
Yeah.
Okay.
It's a sphere.
So, it's a, yeah. When you sphere or any kind of material, but in 3D, right? Now, electric flux over this surface is how much the fields that come out of it, right? If it's negative.
So those electrodes are removed now. It's only the...
Yes.
Okay.
Yes. And let's say this has some
Positive charges.
Positive charges. So, which means you have fields diverging out. Okay. Now, the flux over this surface, right, is directly proportional to what? How much unit for
the D that is coming out?
Yes. D that is coming out is proportional to how much charge. Is contained within.
Correct.
That, which is your
rho.
Right. So, but, I mean, these are electric fields, obviously. Now, if you just take, as you said, a small surface, right? And then let's say you have an electric field here.
Let's say unit surface.
Unit surface. Yeah. Okay. Let's say E. Okay, that's the electric field. Now, the unit normal vector, this surface, I mean, this is not drawn very well, actually. We draw this. Again, not. I'm trying to draw something novel to this surface. Okay. And you have an electric wheel here.
Yeah.
And this is your unit vector. So, any flux that comes out of here then is what?
So, the unit vector is 90 degree to that small plane that you have drawn.
Yes, the unit vector is to that electric field vector, right? So, the flux then is what? Should be E.
Epsilon. Yeah.
Cos theta. Okay. The flux coming out of that.
So, what you're saying is, what is the amount of electric field in the direction of unit vector?
Yes.
Or in the direction of normal?
In the direction of normal, sorry.
Yeah.
Yes. Yeah. Because there are many
Yeah.
electric fields. But if you take something very, very small.
Yeah. So, that is this dot product.
That is. Well, no, dot product is how much it changes, right? At a very small point like this. Okay. Times the permittivity is then your volume charges. But then you're right. So if you take a very small volume like this, then how much the flux comes out is related to then what's the volume charge density inside the material.
Correct.
Right. So that's basically Gauss's law for electric fields. Now, Bobby, you probably heard of something also called relative.
So, one moment, this theta is the angle between that n vector and...
Yes, this is theta.
E?
Yes. Now, again, depending on the surface, that angle will change, right? And depending on the fields coming out of the surface, right, that angle will change.
Yeah. So, this is just the component in
the normal direction. Yes. Because somehow we need to get it into a reference frame, let's say, which is why we are taking the normal component of the electric field. Because the electric fields will be everywhere here, right?
Correct.
What else? So, the more charge you have, obviously, the more flux you have.
Correct.
Right? Which is basically what this is saying, right?
Yeah.
E is proportional to rho.
Yeah.
Okay. Now, I've only drawn positive again.
So, now there are some negative charges. The amount of field that is coming out will reduce.
Yes.
If it has same amount of positive and negative charges, then for the entire volume, nothing will be coming out.
Yes, because positive charges terminate at negative charges.
Yeah, or vice versa.
Or vice versa.
Yes.
Or vice versa. Yes. So in this case, then there'll be nothing combust. I don't know what kind of.
Then the divergence for that whole volume or the whole surface will be 0.
If it's evenly matched.
Yeah.
Yes. Okay. So that's the first.
Yeah, I've got some idea about what is. So if there is, I think the amount of electric field that is coming out is a function of the charge
density
present in that.
Yes. The net charge.
Yeah.
Let's say. Yeah. Right. Because let's say you have more electric fields coming in, right? Then let's say you have a negative charge, right? Negative fields coming in. So then these will start terminating at
here,
right? Or the other way around. If you have this minus and positive charges coming in, so what comes in, then if you compare the net flux, what comes out will be less than what comes in. If this is negative, right? And you have positive charges because they will come and terminate here, and what comes out of that surface will be less. But essentially, the whole point is, this looks complicated, but it's basically taking the derivative in.
So maybe the students can look at the integral way of representing
also.
Gauss.
Yes. There's also, yes. So all these equations that we'll talk about has an integral component as well. Yes. So that's right. So in summary, field produced diverges from positive and charge and converges upon negative charge. Any field passing through any closed surface, right, is proportional to the total charge contained within that surface. Okay. And then larger the electrical polarization, larger is this epsilon, which is your material electrical permittivity. And divergence is basically the limit of flux, as you said, through a very, very small point, surface surrounding the point. Okay. Which we saw earlier.
This permittivity for air.
So, which we call E0.
Epsilon 0.
Epsilon 0, electric permittivity is, maybe I get the feeling you know this because you are very good with numbers. I mean, I think even the last few weeks throughout the course, when there were these constants, you would say, blah, 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 blah. And today you said Earth's magnetic field is about 65, 70. So, I get the feeling that you know this.
Yeah, I think it's 8.854 into 10 power minus 12.
8.8544. You're absolutely right.
No, farad per meter. Yeah,
farad per meter. Now, you also probably heard of something called, when you talk about materials, you probably heard about relative permittivity.
Yeah.
Right?
So we say this is with respect to air, how good is it, how good or bad it is.
Exactly.
Usually how good it is.
Exactly. So we'll see that later on when we see electrical field sensors, this permittivity value is very important.
Yeah. I think for water, for example.
You know
I know. Epsilon R is about 80. 80. So water is a very good, permittivity is very high.
So it's So if people pass, it will align the orient with the electric field.
Yeah, while maybe paper or
some metals.
Or cloth or those kind of materials will have slightly higher than 1, 2, 3, 4, 5, that range, not very.
Right. So, this is for water, you said, no?
Yeah.
So, basically what this, relative permittivity, right? This is, cannot draw here. But basically what ER, the relative permittivity is the permittivity of the material divided by this one.
Epsilon 0.
Which is for air. And I guess there are tables that give this relative permittivity for a lot of materials.
Yes. And it's also sometimes function of frequency.
Yes. So here we assume that it's one number, but you're right. This will change.
But for water, for wide range of frequencies, it's 80.
Oh, okay.
80 or, I mean, somewhere around 80.
Right.
Between 75 to 80 or so.
What is a material that you can probably think on top of your head where it changes a lot?
Because I have done some measurements earlier for ice.
Ice?
Yeah, for ice, actually, for low frequencies, it's close to 80. But after some 20 kilohertz or more, exact, I don't remember, it reduces drastically.
Oh, and what is the reason? Because it changes its...
I think whatever drawing that you're given is not aligning after the that frequency.
So it changes a lot.
Yeah.
I see. Okay. So that's basic the first law of Maxwell.